we want to find the inverse Laplace transform of this function here, which I'll just call f bar s for convenience. Now, at first sight, because of this root s, you might think that this has a branch cut, but in fact it doesn't. And this is easy to see if you consider the expansion of cosh u. So cosh u is basically the same expansion as cosine, except it's all plus signs. So basically, when you expand cosh u, you've got squared to the power 4, you've got even powers. So something like x root s turns into x squared s squared. There's no square root anymore. So although it looks like it has a branch cut, in fact it doesn't. This is there's no discontinuity along the real axis. So we can just go ahead and this is given simply by, we can just quote the formula. Since there's no branch cuts, we can just simply quote the formula that it's equal to the sum of the residues of cosh x root s times e to the st over s cosh root s over all singularities, all poles. So we need to work out where this function has poles. So the poles are going to originate obviously from this term here. We're going to have poles, a simple pole obviously at s equals 0. So we have poles, I should say simple poles at s equals 0. And also when root s is equal to, so where does, so cosh has zeros at n plus a half pi I. So therefore, at s equals, taking the square of this, we got minus I squared. And I should always write. Now, just one little thing to be careful of here. I'm only going to write n from, I'm not going to say that n has, well, strictly, of course, this has poles. Okay, well, this square root okay, what I'm trying to say is, yeah, okay, so if the square root, yeah, okay, so strictly when I've written it like this, the n can take on any integer value, like this. But when I square this to work out where the simple poles are, I have to be careful because here n equals 0 and n equals minus 1 would give me exactly the same value. So I don't want to double count the poles. So now I have to change this to n is just the non-negative integers. Okay. Because I don't want to count these poles twice. Okay, there's only one pole at s equals minus n plus a half squared pi squared. Okay, so I don't want to double count. So that's quite important to think about. Okay, so now I need to work out what the residues are at these various places. So the residue of f bar e to the st at s equals 0 is where if I just use P over Q, so I've got at s equals 0, that's cosh is 1, cosh is 1, and that's e to the 0 is 1, so that's just equal to 1. And running out of space, so residue of f bar at s equals minus n plus a half squared pi squared is equal to, so now I use this, this is my P and this is my Q, so I'll end up with cosh x and then square root of this, so I get, okay, so this will give me, the square root will give me an I, so cosh of I something is the same as cos, so I may as well just put that right in there. So I've got cos of x times n plus a half pi, maybe I'll put this the other way around. I've got e to the minus, so s becomes this, so it's e to the minus n plus a half squared pi squared t. This might start to look familiar if you've done anything to do with Fourier series and solving heat conduction problems. This is starting to look like a Fourier mode here. And on the bottom, so what have I got? I've got, so when I differentiate the cosh, I'll keep the s, because that's just going to give me a minus n plus a half pi squared pi squared, and when I differentiate the cosh with respect to s, I'll end up with, okay, no, I shouldn't have kept this s. So, sorry, when I differentiate the cosh, I'll get 1 over root s, so that gives me a root s. Okay, so I'll get a root s times a half, so I get a factor of 2 upstairs, and times shine root s. So the root s will, as in this case, just give me I times n plus a half pi I, sorry, plus pi, and then I've got shine. So the shine of this will give me sine of n plus a half pi, so times I. So I get another I, and I'll get sine of n plus a half pi. So what does that all give me? Now I forget where this minus sign came from. Yeah, that minus sign was a mistake. Okay, so I've got I times I, which gives me a minus sign. I've got sine of n plus a half pi. Okay, so going up here, this is 2 cos n plus a half pi x e to the minus n plus a half squared pi squared t. Right, so on the bottom I got n plus a half pi. Okay, so then this is minus 1 to the power n. Okay, when n is 0, this is plus 1. When n is 1, it's minus 1, and so on. But I've got this one, I've got an extra minus sign. So in the end, I've got a factor of minus 1 to the n plus 1 down below. Okay, so that's the residues at these points sorted out. And the final answer is just simply the sum of all of those residues. So we end up with f of t is equal to the residue at 0, 1. And there's different ways we can write this. I think I might just leave this as a minus sign and leave this as the power n here. So then we have an infinite sum, and remember that n is from 0 to infinity. So I might, just to make it look a bit nicer, I'll multiply top and bottom by 2, so I've got 2n plus 1 in the bottom. That gives me a factor of 4. I've got this factor of pi. Oh, sorry, no, there's a pi. So 4 over pi, the sum from n equals 0 to infinity. And then we've got this minus 1 to the power n times cos n plus a half pi x I've multiplied top and bottom by 2, so this turns into 2n plus 1. The pi I've already taken out. And that just leaves me with this exponential bit. So that is the final answer. As I said, if you've done Fourier series or analysing heat conduction problems, for example, then this looks somewhat familiar, looks like a solution. Yeah, I've written as f of t obviously has it's a function of x as well. But